If I asked you to mix together red and green paint, what color do you think you'd get? Most people would say brown. But what if I told you that red and green can actually make a reddish-green color that nobody can see? When people see colors, there are many processes happening in their brain to create the perception of color. The process starts with the cells in our retinas called photoreceptors that detect the wavelength of the light we see. There are two kinds, rods and cones. Today we're going to focus on the cones since they are the ones that allow us to see in color. There are three kinds of cones, each most sensitive to a particular wavelength and thus a particular color. Those three colors are red, which is the long wavelength, green, which is a medium wavelength, and blue, which is a short wavelength. When stimulated, these cones produce the perception of colors. This idea is known as the trichromatic theory. Now you may be wondering why we're able to see colors other than red, green, and blue. We can see those colors because of the combinations of stimulation of the different kinds of cones. The colors red, green, and blue are just the peak sensitivity of those cones. This means that each cone has a range of wavelengths and thus colors that they can detect. When stimulated in certain combinations, we can see other colors. Take yellow, for example. We can see yellow when both red and green cones are stimulated, since yellow is part of both the red and green cone color range. Now, this theory doesn't explain many parts of color vision, including the fact that we can't see the reddish-green color, so we have a second theory known as the opponent process theory. Basically, this theory states that the photoreceptors in our eyes are linked together in ways that form opposing color pairs. Those opposing pairs are red and green, yellow and blue, and black and white. These opposing pairs are what prevent us from being able to see the reddish-green color. You see, when one color of the pair is active, the other is inhibited. This means that we can't experience both colors in the same spot, which is why we can't see the reddish-green color. This theory also explains some of the other phenomena in color vision. Have you ever seen one of these images? The complementary after effect of looking at one of these images can be explained using the opponent process theory. Basically, when one side of the pair is used for a long time, it becomes tired, so the inhibition of its counterpart reduces, so the other side of the pair becomes more active relative to the original, resulting in its color being seen. I like to think of it like a race. One color was going hardcore at the beginning but gets tired. The other color sees them getting tired and starts to speed up a bit, resulting in a higher relative activity level. So the other color passes the first color by and wins the race in the end. These two theories work together to help us understand how color vision works and why we aren't able to experience every color out there. So now you know the colors of the world aren't just limited to the ones in the rainbow.